Let's talk about water. Water, as you may know, is two hydrogens bonded to an oxygen, H2O. Oxygen has an element number of 8. That means it has 6 electrons in its outside or valence electron shell. It wants 2 more electrons. Hydrogen wants 1 more. So the two hydrogens get together with the oxygen and shares with the oxygen. Now, because oxygen is bigger than carbon, it can keep the electrons a little bit longer instead of stealing them. And so what happens is the electrons zip around hydrogen once, twice around oxygen, once around hydrogen, twice around oxygen, once around hydrogen, twice around oxygen, so that what happens is the molecule gets a slight positive and negative charge. Oxygen gets a slight negative charge because the electrons are spending more time around the nucleus of the oxygen, and the hydrogens get a slight positive charge. We call this a polar covalent bond. Think of it as the poles of the Earth. The Earth is a big magnet, and it also has a negative pole and a positive pole. Now, because water has a positive and a negative side, if you will, positive and negative pole, it forms bonds with other water molecules. The negative oxygen is attracted to the positive hydrogen, and so on and so on. And we call these hydrogen bonds. Don't get confused between the bond, the covalent bond, the nonpolar covalent bond between two hydrogens in gaseous hydrogen, and the hydrogen bond between molecules. Now, hydrogen bonds can form between any molecules where there is a hydrogen bonded to an oxygen or a hydrogen bonded to a nitrogen. Those are the ones that you need to worry about for this class. Now let's talk about what happens when you mix water with molecules that are not capable of hydrogen bonding. Here we have an example of a string of carbons, non-polar covalent bonds between the carbon and the hydrogens that are attached to it. And we have a bunch of waters. Well, the waters, because of their polar covalent bonds, they've got the slight positive and slight negative charges. They're attracted to each other. So this one comes over and says, hey, I can form a hydrogen bond with you, and it's all happy. And this one over here is saying, oh, well, don't leave me out of the party. And the carbon molecule is saying, hey, you're stepping on my toes. And it keeps getting more and more crowded. Hey! And it can't form hydrogen bonds with the water because it doesn't have an oxygen bonded to a hydrogen, nor does it have a nitrogen bonded to a hydrogen. So what happens is it's excluded by the water. Now we call this hydrophobic interactions. Molecules that are incapable of forming hydrogen bonds are excluded by the water that wants to hang out by itself. Okay? Kind of sounds like cliques in high school, doesn't it? Now, molecules that can form interactions, hydrogen bonds with water, are called hydrophilic. Philic meaning loving, hydro for water, so they're water-loving molecules, whereas molecules that are excluded by water, that can't hydrogen bond, are called hydrophobic or water-fearing. If you take salt and put it into water, what happens? It disappears. It dissolves. If you taste the water, it's still salty. The salt is still there. What's happening on a molecular basis is the water, because it has a slight positive and a slight negative end, can interact with the ions of sodium chloride. Okay, so here's what's happening. The sodium ions say, hey, hi, water. And the chloride ion says, hey, hi, water. And they separate. We call this dissolving. Okay. Now, water can do this because of its slight positive charge and slight negative charge. It can also do this with molecules that are hydrophilic. Okay. So, for example, sugar is not an ionic compound, but it does have oxygens bonded to hydrogens, so it can do the same thing. So when you add sugar to water, it dissolves. Okay. Now, we call this a solution, either a salt solution or a sugar solution. The solid stuff that you put into water we call a solute, and we call water the solvent. You put a solute and a solvent together and you get a solution. Now, water is important because it's the universal solvent. It can dissolve most things. And your cells exist as a water solution. So it becomes very important in biology. From here, we're going to discuss what else happens in different types of solutions. There are two types of ionic substances. Those like hydrochloric acid that release hydrogen protons, hydrogen ions, into water when they dissolve. We call this an acid. That's why we call it hydrochloric acid. There's also those that when they're put into water, they release a hydrogen-oxygen bonded ion. We call this a hydroxide ion. And these have a tendency to combine with any hydrogens that are floating around in the water and form more water. We call these bases. So an acid is anything that releases hydrogens in solution. A base is anything that removes hydrogens from solution, namely if it has a hydroxide ion. Or, we'll get to this later on in this chapter, an ammonium ion. Okay. Now, if you combine an acid with a base in solution, they will combine and make a salt and water. These hydrogen and hydroxide ions get together to make H2O. The sodium and the chloride get together to make sodium chloride. We call that a salt. Both acids and bases are important in biology, as well as salts, since your cells are composed of both. And your cells are very busy keeping the balance between acids and bases. To measure whether something is more acidic or more basic, we have a pH scale. It's based on how many hydrogen ions, how many free protons are floating around in the solution. Now, this is a scale that goes both up and down. So let's start at the middle, or the starting point. This is where we're considered to be neutral, where you have equal numbers of hydrogen ions and, in this case, hydroxide ions, or ions that are taking hydrogen ions out of solution. This is a pH of 7. Pure water is considered to be a pH of 7. Now, as we go to smaller numbers or down the scale, unfortunately the scale has it going up, and as the pH lowers, you get increasingly more and more hydrogens. So if you look at the substances that are listed, as they get more and more acidic, you can recognize that. They get, when you taste them, more sour, more corrosive. Okay. So milk is just a little bit acidic. Urine is just a little bit more acidic. Tomato juice, it's kind of tart, unless you've got some nice garden fresh tomatoes. And wine, grapefruit juice, lemon juice, stomach acid is a pH of between 2 and 1. Now going the other direction, this is where you have fewer and fewer fewer and fewer hydrogen ions versus hydroxide ions or anything removing hydrogens. So human blood is just a little bit basic, or alkaline is another term for it. Seawater is a little bit more alkaline. Milk of magnesia, that's back, and most of you are probably not familiar with that. They still sell it, but use it for an upset stomach. So if you have too much acid, you drink something that's a little bit basic to neutralize the acid and create salts. Ammonia, you wouldn't want to drink that. Household bleach, wouldn't want to drink that. And you get oven cleaner, that's our sodium hydroxide that we had in the last slide, and lime water. Okay, now, your body needs to stay at a pH of just a little bit alkaline. So it uses buffers to maintain that pH. Buffers are salts, or more usually weak acids or weak bases that can adjust to an increase or decrease in hydrogen ions by either taking up hydrogen ions or releasing them.